The clicker also works. It goes in this direction. Cool. So, I'm Roland Kuhn. I'm CTO and one of the 3 founders of Actix. We make software for factories. This kind of also might be a hint for what this cryptic title means. But in the end, this is a presentation about the Internet of Things. And my favorite rant will start it off. So, when you hear Internet of Things, what do you think? I mean, I think of this light switch that I don't need to get up and walk to and press anymore. So I touch something on my phone and then the light turns off or on, if I'm lucky. Now, I might be a grumpy old man for saying that I don't really care about that, because I'm totally okay up and walking to the switch and switching it on and off. But more importantly, this Internet of Things that I just described currently works by sending everything to the cloud. What is the point really? I mean, I have my phone here, I have my light switch here, I have a network in my home. So what does the cloud have to do with any of this? Not much, really. So why is it needed? It's not needed, it just is not helpful. Let's illustrate that with another example where it becomes even more obvious. So what do I mean by Internet of Things? I'll decompose that using normal English dictionary meaning of the words and then work towards what I think the Internet of Things should be. So it starts off not with one thing that's connected to the cloud, it starts off with things, plural. So there are multiple things here. And it says of things. So we take together these things and they form something. And there's a network of things. So these things form a network and they collaborate. They do something together. Yeah? That's the first basic thing. And then we put this inter in front of it, and it means, I mean, the internet is a network of networks. It is the globe-spanning super network of everything that can communicate today. So if we say Internet of Things, it means we have all these networks of things that collaborate on purposes, and they are all able to communicate at a broader scale. So that's what I think Internet of Things should mean. It means you have the things, they collaborate, and we have a network for it. Now, how could that look like in a home? I don't have that. I'm not sure when I will have it, but I could imagine having, for example, a delivery box somewhere at or close to my home, where a drone can deliver stuff, so that I don't need to be at home when the stuff arrives. And that there is no very stressed human driver trying to meet all the demands of delivering parcels to people. So why don't we do that? Now, if you have this picture in mind, so I have my house, and there is a box like on the roof or near the porch or somewhere, and there's a drone coming flying and trying to deliver a parcel that I ordered. Now, this box is a thing. There's some software running on it, there's a controller on it, it will have some sort of a hatch or a door that it can open, it will need to have some safety equipment that this doesn't close when I stick my hand in, so there will need to be some controllers in that. It will be software driven, it will have software in it. This box is owned by me, ideally. I'm fond of owning things. So this box is owned by me, so it's my software, ultimately, that it fulfills my purposes here. Now the drone comes flying from over here. I do not own that drone. It's not mine. It may belong to Amazon, for example, or some other company. So this drone comes flying, and here is my delivery box. Now they need to somehow work together to get the parcel into the box. How is that supposed to happen? If you picture it, I mean, just make it look a bit more human-like. So the box has a personality, right? The drone has a personality. It's just people. How would they do it? Well, the drone would come flying and say, here I am, here I am, here I am. And then the box says, oh, I'm here, I'm here, I'm here. So they find each other and they agree based on, for example, signatures, digital signatures, trusted certificates, that this is in fact a drone owned by Amazon. I trust drones by Amazon. This is a box signed by Amazon, so the drone trusts the box. The drone might carry a certificate for this delivery that I have signed, so that it's clear that I actually want the thing that's on the drone. So they exchange all this information. And then the box says, okay, this is all correct. I open my door, drone puts in the parcel, flies a bit away, says, now I'm away, the parcel is in there, box confirms, yes, I have the thing, closes the door, transaction is done. This is how we would describe it if we were talking about machines like people. And I think this is fundamentally the best way, or the only way, at least I can think, about programming. I need to describe what is supposed to happen in plain English, as if it was actors, human actors carrying out things, and then I need to make sure that I describe it in such terms that I could explain it to not very intelligent people, because machines are not really intelligent. They are just quick. So this is how it would work. Now, the Internet of Things here means this whole interaction should happen locally. There's like billions of drones on the planet, but only one is interacting with my box at home. This is what I think the Internet of Things should be. Now, let's switch gears. So where do we apply this? We apply it in factories. And factories are a very nice place to illustrate the effects of this. Who here has been to a factory? Some hands, but less than 10%. So that's usual. We get all our things out of factories, but few people actually have visited factories. When you think of a factory, you see something like from the news, like a Tesla factory that's all very clean and all robots and so on, producing these cars. But most factories actually look more like that. You have some material that you turn into more valuable material by putting in other resources and labor and electricity and so on. And hopefully the more valuable material then is so much more valuable that you can pay for all the differences and have something left over, which means the factory is making profit. And these processes, sometimes, this is a glass manufacturing machine, and manufacturing glass is particularly dirty. You have all this stuff flying around, grease and so on. And there is this guy over there who is setting up the machine. So the machine and the person are collaborating on producing glass bottles in this case. Now, what is very important in a factory is you pay money for the person being there, you have paid money for the machine, so you have the depreciation. So just things being there cost money. You need to run the process of turning inputs into outputs in order to offset that and make profit. Otherwise, you make losses. This immediately means time is money. Whenever you introduce something here, some technology here, and it leads to downtime, it immediately leads to losses of money. So this makes reliability the top concern. It needs to work at all times. Also, factories are a nice place, a different place than if you, for example, want to test out installing apps on Android devices and getting people to use your new social network or things like that. Because in a factory, there are many dangerous places. You don't just do whatever you like. You don't step where you're not supposed to step, because you know that in the factory you need to abide by the rules, otherwise you put yourself and others in danger. So a factory is a constrained environment in which you can more easily install software than on a client, in a client setting where every customer puts it on their phone and then does whatever they like with the software. So in a factory, people are bound to follow the rules for safe preservation reasons. Now, what do people use in factories so far to run all these processes that, for example, I need to do this now, the machine needs to do this, these are the setup parameters to make this machine produce the right kind of glass bottles in the quality we like. It's mostly done on paper. Paper is extremely resilient. You can take a paper and you write on it with a pen. You need a paper and a pen. You write on it and then you switch off the Wi-Fi. What happens with what you have just written? It's still on the paper. You switch off the electrical power, it's still there. You can still read it. You can crumple it, put it in your pocket, take it back out. It's still there. The paper is extremely resilient. Try that with an iPad, it doesn't work. So this is why factories are using paper today, and this is the reason for the title. If you want to replace that paper, you need to create a system that is about as reliable as paper was. And that is a huge hurdle, and that is why I think this Internet of Things is what we need in this place. So picture this. I mean, I'm now abstracting, so the pictures are not as dirty anymore. To focus on what's happening. So we have a machine here. It might be a machine producing valve housings, applying lots of tools. So this machine is very intelligent on the inside. Or it has real-time software controlling what's happening on the inside, highly automated process that we as a human cannot even follow when we look at it sometimes. So it's ultra precise. It machines things with a precision of a few micrometers. So yeah, this is an awesome machine on the inside. But on the outside, well, we can look at it and we see, yeah, there's something, and then it's finished, and then the part, we can inspect the part, but really it's not that accessible to software from the outside at this stage. Now, there's a person walking by here with a tablet. The person and the machine need to collaborate. The person, for example, needs to say, this is the order that we are manufacturing now, these are the settings, this is the CNC program that we need to run, so then the machine can start. The machine has been instructed what to do. We have recorded what order it was and when it was started. Now, when the machine does its job, it might generate new information, like, oh, the tool just broke. I'm interrupted, so process is stopped. Please come fix me, because I'm a machine, I'm dumb, I cannot fix myself. So human needs to come. The human goes there and does quality inspections and sees, okay, this is machined correctly, yeah, that's nice, but then next shift someone checks and there is a small deviation, so people need to change the program or check for broken materials, stuff like that. So there's communication going on between the human and the machine. The machine generates information, like what it is doing, and the human generates more high-level information, like what the machine should be doing, or confirming that everything is all right. So this is the very first step of replacing paper with something here that's the communication between the tablet and the machine. But thinking a bit ahead, where are we going? We might be going to such a place where, so the job that I just described, the person, it becomes more and more difficult to justify paying a person to do these jobs, because if we can automate it, if we can, like, the quality inspection can be automated by a drone flying over it, noticing that the tray is full of pieces produced, then a robot can come by, pick up one of these things that have been machined and put it into a measurement station, and then the measurement station says yay or nay. So these workflows are very, very simple. You don't really need a human brain to carry them out, and you don't need the human hands and rest of the body to do this. We have the ability to do this by robots, to automate that, which means the value creation in this whole process is getting so low that in the end you cannot pay a human as much as needed to sustain their life. So in this sense, humans are going to move up in the food chain and do more intelligent things than taking care that a machine is doing what it's supposed to be doing. But if you look at this picture, there's a lot of communication that needs to go on. The machine is producing all the information about what it's doing. The drone might be producing information about the quality inspection pictures and also about facts like movements recorded. The ATV here, the transport vehicle at the bottom, needs to come there when something needs to be brought to the warehouse, and so on. So there's lots of communication that is needed between these 4 devices in this picture. But you might have a factory that has not one group of these 4 devices, but like 1,000. But you only need these 4 to communicate. These 4 collaborate on a common purpose, so they need to communicate. There is no reason why they should communicate via the cloud. And there is good reason for keeping the number of components that are needed for all this to work to an absolute minimum. Because everything you put into the path, any network segment, any software or hardware component that you put in between these 2 of these machines reduces the reliability. Everything can fail, everything will eventually fail, it's just a matter of the rate. And if you have more things that can fail, you have more failures, you have more downtime, you reduce productivity. So most of the factories, just for background, have very low margins. So they produce and they make a profit about a few percent, like 2 or 3% of their revenues. So if you introduce 1% of downtime by failing any of these components, you basically take away half the profit. This is why it's so very important to keep this working always. And this means keeping it local, because then you reduce the likelihood for something to fail. So, this was for context. Now, how do we want to communicate? Because all these things need to collaborate. How do we make that happen? The answer that we're applying at Actix, and that I strongly believe is the right one, is via an event log. Events are extremely nice because, for example, the machine says, I have produced one piece. This is not something you need to talk much about, it's just a fact. Or the person down here registers, okay, this order has just started, or this has been finished, I confirm it, I sign the quality inspection, whatever. These are just facts, and you can just put them in the log. And then whoever wants these facts can read them from the log. You don't need any complicated ACID transactions in databases and stuff like that. You just put them in the log. Nobody is allowed to ever remove any facts. You just record them. So this robot over there has a failure, and so you just send all the sensor data streams, the 3D and 2D cameras and everything, and persist them in the log, and then people can look at it later and figure out what happened. So this event log is extremely useful. You can do also other nice things. Yeah? So if you want to deploy software on all these tablets, computers, machines, and so on, you need a system for running that. You need infrastructure, you need to check the health of the devices, you need to track the battery charge levels to see, okay, this went from 100 down to 0 and now it's offline, so perhaps someone has unplugged the power, stuff like that. So there's also all sorts of things you want to track in order to reliably run such a system. It's perfect to put all that in the event log too. So you put the health metrics there, you record everything that's happening, and you put it in your log. That's totally awesome. Who here has worked with an event-sourced system? That's fewer hands even. So event sourcing is basically this. The truth that you store is not a database row. The truth that you store is just the facts as they happened. So let's take an example. The human here needs to press a key on press a button to say, this production order shall start. So this production order is now running from the viewpoint of the machine and the computer and the human. So what I have done is I had the previous state, order was just created, not running. Now I press this button and I apply the event to update the state, And locally on this computer, I know it's running. Yeah, so I derive the state by applying events. So if I press the next button of, please interrupt this, then the event is, the activity has been interrupted, and now locally the state changes, and something is red on the screen, probably someone got a text message because something has been interrupted. So event sourcing means you only store the events. You do not store the state that you derive from them. You start with an initial state, and then you apply the events to the state to arrive at your current thing. By the way, this is, who here knows Bitcoin? I mean, not only the term, but a bit about how it works? Somewhat, yeah. It's a similar principle. You start out with an empty wallet, and then you do transactions. The transactions are only what is recorded in the blockchain, not the state. And then you get your current wallet by applying all the events, all the transactions that have been recorded. So same thing here. So you get this event log, and it has recorded all the things that has happened. It has not recorded the states, but the events. This is pretty awesome, because it allows you to time travel. Have you ever felt the need to figure out what your system was like last week on Thursday at 1300? In a factory, that can be extremely handy, because something went wrong then. So you just look at the event log, and you cut away all the events that were after last Thursday, 1300, and you run your state machines up to that point, and then you know exactly what the factory was up to at that instant in time. This is really nice. You can do that with any point in time. So that means if you use an event log with immutable events that you never, ever mutate, then you have a perfect audit log as well, and you know everything that has happened in your system, in this case in the factory, since the system was introduced. So it's totally awesome. Yeah, we call it the pen-lonely log, yeah, and it's appearing in many places these days. It's really an awesome thing to have. Now, I said things need to be ultra-reliable. These 4 machines on the previous slide, they are working together, and only the 4 things collaborate, and they shouldn't care whether something else failed over here. So it's ultra resilient by being small groups of machines working together. But now what I've done here is I've put this huge event log thing in the middle. Isn't that really bad? What if the event log fails? Nothing works anymore. If I cannot put stuff into the event log, I cannot record facts, I cannot progress. If I cannot read from the event log, I don't know the state of the world, I'm completely helpless. I cannot make decisions. I cannot show anything on the screen if I don't read the event log. So this is really, really bad, because just cutting away the event log makes all these very nice edge devices that were so nicely collaborating completely useless. Unless we have a log that is always available. So let's enumerate the properties that we would like to have from this log. Always available for writing. That's what I meant with the pen and the paper. I need to always be able to locally record what I'm doing. I need to be able to write on that paper. No matter whether someone else is up or down, or whether I can reach some other node, or Wi-Fi could be off, right? I just have a tablet, and I'm pressing a button, and that button press needs to be recorded. There is exactly one place where that can be recorded, and that is locally on the tablet, because Wi-Fi is off. So always available for writing means I can always record facts. I may not be able to communicate them, but at least I've recorded them as best I can. The second one is, I want to update my UI. So I press that button. Now, for example, the status should change from the activity was pending to the activity is now running because I pressed start. That means I need to always be able to read from the log. I need to at least be able to read what I have just written. Again, you look at the paper, you see what you've just written. That's really natural. We are very much used to this. We are not used to writing on a paper and then, oh, it's not there anymore. That's not how it works. So, always available for reading, at least the local ones. If I cannot communicate, I cannot see what anyone else has written, but at least I can see what I have written. By the way, it's pretty clear that this means that the system will not be strictly or sequentially consistent. We cannot form consensus this way. I can switch off the Wi-Fi, I only have this device, I record information on it. Now, the order that I'm working on was not started before, so the whole system knows it's not started. Now I have this tablet which is out of Wi-Fi range, I press the start button. Now on this tablet, the order is running. In the rest of the system, the order is not running. It's an inconsistency. But it cannot be avoided if we want the log to be always available for reading and writing, so that we can locally always make progress. So yeah, this is the first very important choice. The system will not be strictly or sequentially consistent. It will be eventually consistent. That's the next point. We want it to eventually reach a consistent state, because otherwise we really go insane as a programmer. As a programmer, you write down your logic, like when this happens, then that state change, when that happens, then that state change. So when you press start and you press, I've done 1,000 pieces, and then you press finished, well, in the end, the order is finished with 1,000 pieces. No matter at which location in the network I ask, I should get this answer. It needs to be eventually consistent. So this means that there needs to be synchronization. So whenever the Wi-Fi comes back on, or the device is plugged into the power outlet again, and then starts up again, things start communicating, things start synchronizing, and once everyone has seen all the same events, so once we have communicated all the log, everyone should come to the same conclusions. It should be self-healing. One thing I forgot for this one. This needs to work without the cloud, by the way. This needs to work locally. I say this, so who here is using Google Docs? Probably almost everyone, right? Google Docs is totally awesome. I love it. It's the only thing that really works on German trains, because in Germany we don't have this thing called internet, especially when you're on trains. So you can work, and sometimes it synchronizes, sometimes it doesn't, but it's extremely robust. It's totally awesome. But it has one flaw. So I have my phone and I have my computer. They're in the same network, or they're coupled by a Bluetooth, or they can communicate, but if I'm not connected to the Google servers, Google Docs won't sync. No? For a factory, that's not good enough. We need this to be as well working as it can be. One reason here, well, very simple reason is, if you depend in your factory operations, in your livelihood of the factory, on the internet connection, then that makes you open for an attack. Someone could just flood your DSL connection, make simply the internet traffic service unavailable by overloading the DSL connection. And if they do that with a large botnet for 3 or 4 days, then there goes your yearly revenue. Your yearly profit, sorry. So that's not good. So this all must work without an internet connection. It needs to work in the Internet of Things, between the things. Yeah, and another one is, you might have a tablet that someone, I don't know, it ran out of battery, then it didn't work, and people didn't really care, put it in a closet, and someone takes it back out a week later. So you don't really know when someone will want to consume these events, when someone wants to read from the log. So the reader needs to be able to choose the delivery. This is not some broker where you send your messages and then you keep the last 1,000 or so. No, you need to really buffer, ideally forever. Because the log is everything. The log is just the state of the factory for all time, and you just keep it. You can analyze it and so on, but you can also bring a tablet back online that has been offline for a month, and it will still work. It will get all the events, because the event log is persistent. So, yeah, can you picture this log? This log cannot be a Kafka. This log cannot be a central instance. It cannot be an asset database. It also cannot be in the cloud. This log needs to be between devices. It needs to be stored in the network between my tablet and my machine connector and perhaps a VM that runs next to the ERP system. So this needs to be a peer-to-peer thing. Now, in a peer-to-peer thing, so let's say I identify myself now with the tablet that I'm holding. So I have this knowledge state of the world shown on the left-hand side. I have these 5 events on the left-hand side. And the Wi-Fi was off. And now the Wi-Fi is on again. Now I get 2 new events, the orange ones at the top. Now it's peer-to-peer, so I'm not special. Others are not special. I just get these events whenever I can get them. Now there's one very basic question. Where do we put these events in the order? So on the left-hand side, we see the first obvious choice. So we just put the events at the end of the local copy of the log. Everyone will somehow have to construct a copy of the interesting part of the log that they want to see. So if we put these events on the left-hand side at the top, I would call this local discovery order. Because the order in which events end up in the logs will be different from one tablet to the next, to the machine gateway, to a computer on a robot. They will all see the same events eventually, but they may see them in wildly different orders depending on who was communicating to whom and when. This means if you want to program a state machine here, and you want to have your sanity, which means you want it to be eventually consistent, you need to choose a model where applying the same events results in the same state, regardless of the order in which you get the events. This is kind of hard. Can you picture that? So you get something like start, I logged 1,000 pieces, and stop, that's really what happened. But if you get them in inverse order, you should still come to the same conclusion that this order is now not running and has produced 1,000 pieces, even though the last event you got was started. This is kind of difficult. There are certain data types that solve this problem for certain data structures, like sets, maps, counters. They are called CRDTs, conflict-free replicated data types. They operate based on commutative pieces of data, operations or deltas, that you can apply. So the data type itself figures out how to apply these events, regardless of how the events actually arrived at the data type, and then arrive at the right answer. So you add something to a set, and you remove something to a set, and then it should stay removed, regardless of how the communication worked. And there is some deep magic in there, and very smart people have figured out how that works. But I don't think, I mean, I can't do that in general, right? It's a very special approach that you need to take here to make sure that your event-based system will be eventually consistent. On the right-hand side, I have a different proposal. That's what we do at Actix. I would call that eventually consistent order. So the log itself is constructed such that when everyone has all the events, they will end up with the very same log. The order in which things appear in the log is deterministic. It's determined by the events themselves, so that you can construct a log that will look the same at all sites. And then you can run your state machine over these events on the right-hand side. And so first you had run it over these 5 events, and it produced a certain state. So the state machine came to the conclusion that the order is running currently, for example. And then you get these new 2 events up there, and you insert them in the right places. And then you rerun your state machine. So you roll back to event 1085 once you got these events, and then you process all of them in the right order. And since that is done at all tablets, all sites, all these devices, in the same fashion, everyone will arrive at the same conclusion. This makes it much easier to program something that is eventually consistent. In fact, you can write whatever you want in your program code. You don't need to care. It will be eventually consistent. It might not be consistent with the real world. Like, there might be a disconnect here. So the order which you choose for the application of the events might not be the actual order in which they happened in the real world, and then your state machine consistently comes to a wrong conclusion, so to speak. That can still happen, but that cannot be avoided, because how can the computer know what the state of the universe is? That's too tough a job for them, at least today. So at least we can make it eventually consistent. So, but we need these numbers for that. Yeah, we need to sort. We need this deterministic sort. We can make that happen without any communication, without the need for any coordination. We just need to make sure that every event can be uniquely identified, and we can define a total order for the events. Total order means I can compare two events, and I always get one is less than, equal, or greater than the other for any two pairs. I can always decide that without any further information, only the two events. So how can I do that? I could use UUIDs for each of the devices, and they are sortable. I can just string sort them. And then I just need, for example, a sequence counter at every tablet. Every event that's produced at that tablet increases the counter by 1. So I have the tablet's source ID, so the UUID, and I have a counter. And no two different events can have the same tuple of these two values, and I can always compare them, and that will result in some ordering. Yeah, is that clear? So you can arrive at an order. That would not be a very useful order, but it's one that works and makes it eventually consistent. You can use timestamps to make it more useful. If you really trust your clocks, which you may or may not want to do with Android tablets, then you can use just timestamps. You can also use logical timestamps like Lampert clocks. So it's clear, you can derive something that you can order, and you can make it such that the system is eventually consistent. Still, you need to think a bit how to keep it in sync with the real world, but there you can enlist the help of humans as well. After the merge, you can see, okay, this order is still running, so it will show up on the dashboard in the factory. People will see, I just closed this thing. Close, and then it's done. So sometimes you can outsource that consistency correction to humans. Okay, so one last thing here. If you look at, so on the left-hand side I said you need to use CRDTs or something similar. You need to use data structures that can guarantee eventual consistency regardless of the order in which information arrives. And for that, the predominant ways of doing that is you apply these as operations. So you put something in a list which is the operation of adding it at position 5, for example. So this is universe A here on the left. The events are not events that you and I can understand. It's just operations. Like put something at position 5 into this list, delete the item with this ID or whatever, and they're living in this universe, which is the closed world of Internet of Things here that manage this data type. It's the set of these devices. They share this log which contains these deltas or operations. Now, universe B over there, I already said it, could be my brain. I might want to understand really what this delta over there means. That's quite hard. That's not what it's meant to be used for. Yeah? The universe B might not be my brain, it might be another system. So this is the closed world of on the shop floor, and universe B might be the back office. I might want to transform these things. If I want to transform the delta, I need to have all the context leading up to this delta, to be able to understand why the delta was emitted, what it actually means in business terms, and then I can translate it. So yeah, this is a bit difficult. This is why I prefer semantically meaningful events. If you have an event log and you record really just what happened, not put this in the list, but this activity was started. That might make it appear on some list, but the activity was started. That's meaningful, people understand what it means. Then you can more easily write this yellow arrow. So I can read it as a human, I can understand what it means. I can also translate it into a different bounded context in DDD speech. Cool. So before closing, I'll just mention that we have not built everything from scratch. There's this awesome technology called IPFS, the Interplanetary File System. This gives us most of the peer-to-peer infrastructure that we need. So device discovery, POP-sub between devices, data storage between devices, it's content rest storage based on hashes. You can just dump your data in, you don't need to know where it is stored and stuff like that. So IPFS, look it up, it's awesome. So the closing remark is that you should take away from this presentation what I think the Internet of Things should be. It's about communication between the things. You should communicate immutable facts that you cannot retract afterwards, that you can trust, so you can disseminate, you can make these facts known widely because they're immutable facts. And then based on the knowledge that you have obtained from these facts, you decide locally what to do next. Thank you.